We're going to finish this section off by finding the equation of a function given 2 points, assuming linearity. So we're going to start with an example that's not contextualized, just so we can see the strategy, and then we'll do something. We'll go back to the demand example. So here's a completely uncontextualized problem. Find the equation of a linear function passing through -1, 4 and 2, 13. These are 2 points. In the previous examples, we were also given the slope. We don't have that here. Pause this video for a moment and just think about how you would solve this. What's the first thing you might do? I'll give you a moment, but pause and think about it. Okay, hopefully there was enough space for you to pause. Here's how it's done. First thing you do, find the slope between the 2 points. Rise over run, right? Once you have the slope, you're basically back in the same position we were in the last video. You have some additional information in the form of a second point, and you can use either point to find the y-intercept b. So let's do that with this problem. So first we'll find the slope. The slope is our rise over run. Notice you have to be careful to be consistent. Our rise is the change in x, so that's 13 minus 4. Our run is the change in y, which is 2 minus -1. Notice since I started with 13 here on the top, on the bottom I need to start with the x that goes with 13, and that's 2. So I started here with 13. That means the 2 goes first down here. And then the second y value is 4, and the -1 here goes with the 4 as points, right? Complete the calculation, you end up with 3. So now we know our slope is 3. So here's our problem now. We have 2 points and the slope. So in some sense, we're in better shape than we were in the last video. So as we did with the second example in the last video, we plug in one of the coordinates, the x and y's for one of the points, into our partial equation and solve for the parameter b. I like -1, 4 because the numbers are smaller, and anything with a 1 or -1 is always nice to work with. So I plug in 4 for y, -1 for x, I use my slope 3, and now I have this equation with my unknown initial value b. 4 equals 3 times -1 plus b. Well, that can certainly be solved. -1 times 3 is -3. Add 3 to both sides, and b is 7. We now have enough information to write the equation down. Right? M is 3, b is 7, so we slide those numbers into our old friend y equals mx plus b, and the equation is y equals 3x plus 7. Now let's look at something contextualized. So we're going to use demand again, but we're going to use some different data, and it's going to be for a different good or service. So remember that Q continues to be in thousands. So let's look at these sentences. The first one says to sell 5,000, charge $57.50. The second one says to sell 10,000, charge $45. No change words here. Nothing suggesting that there's a rate of change in any of these sentences. They're simply points. What you would sell if you charge a given price. So let's look at them as points. Remember, our x's are what we sell in thousands, so that means our x in the first sentence is 5, the price is $57.50. Similarly, the second sentence tells us a point, 10, 45. The key thing to do in whenever you're running into something contextualized and you're assuming linearity, is to look at the data and make sure you interpret it. Is it telling you something about change or a point? Is the change information a rise information or a run information? How can you use that to get a rate of change? That's kind of the name of the game in this scenario. Right? So now what we've done is we've turned this contextualized problem into the same problem we just solved without context. Find the equation of a linear function between 2 points. So we do the same thing. First we find the slope. The slope is rise, which is 45 minus 57.5, over run, which is 10 minus 5. As before, notice the 10 in the run goes with the 45 in the rise. The 5 in the run goes with the 57.5 in the rise. You could do it in either order. You just have to be consistent. Perform the calculations. The result is our slope is negative 2.5. Let's pause for a moment to remember what that means. That means if we want to increase x by 1, we decrease y by 2.5. Remembering x is production in thousands of units and y is our price in dollars, to sell 1,000 more units, we would have to reduce our price by $2.50. It's always good to pause after a calculation to make sure you understand what it means in the context of a scenario. All right, that's the first step. Second step is to plug in a point to our partial equation to find our unknown b. I chose 1045 because they're both whole numbers. 10 is a nice number to work with, but you'll get the same answer if you use the other point. So I plug in 45 for my y, negative 2.5 for my slope, 10 for my x, and I solve for b. Negative 2.5 times 10 is 25. Add the 25 to the 45 to both sides, and we get b is equal to 70. Remember, that's the initial amount. If we charge a price of $70 or more, we're not going to be able to sell anything. That's what that means. Now we have all the information we need to just write down the equation, which is, in terms of x's and y's, y equals negative 2.5x plus 70, but we're in a context here, so let's use variables more suitable for the context. Our price P is y, our quantity we sell in thousands is Q, and that's our x. So instead of x and y, we've got P equals negative 2.5Q plus 70. We now have our equation, and we can make any of the predictions that we want to make. So in the last couple of videos, what we've done is we've seen how to use information presented verbally in order to obtain an equation. And in the first part of video for this section, we saw why those equations are valuable. They can be used to make predictions, make decisions. In the next couple of videos, we're going to talk about how to get these kinds of equations when we're given data, but we're given a lot of data, and there's some statistical noise. So this comes full circle and comes back to our data chapter from the beginning of the course, and there's a little bit of probability involved, although we're not going to have to do any probability calculations to understand what things mean. We'll have to think probabilistically.